We're looking at section 3.6 today. This time, instead of equations, we're going to be solving quadratic inequalities, and we'll also look at a few applications of those. I'd like to start by taking a look at this from a graphical perspective. So here's the problem we're trying to solve. We would like to know when the quadratic function x squared minus 8x plus 12 is less than or equal to 0. What I've done for us here is I've just printed out the actual function, the x squared minus 8x plus 12. And if you look at this, I think graphically, it's relatively simple to see where that graph dips below, or in other words, is less than 0, right? The x-axis represents y equals 0. And therefore, this part of the graph would be less than, or in other words, below 0. Sorry, I picked a bad color since my little program is turning everything blue for us. Let me change that. There we go. See it a little bit better. So that part of the graph is definitely below 0. In order to answer the question, or in other words, solve that inequality, we need to list the interval of x values that corresponds to this part of the graph that satisfies the original inequality. Now notice, right here we'd have x equal 2, and over here we'd have x equals 6. And since the original inequality was not just less than, but also included the possibility of being equal to 0, I'm going to say the interval would go from 2 to 6 and include both the 2 and the 6. So graphically, I can kind of see visually how to solve that inequality. The next question we want to ask ourselves is, what if we didn't want to solve it graphically? What if we wanted to solve analytically without looking at a graph? Well, what would we need to know? Take a look at this graph one more time. And I want to think for a minute about the 2 and the 6 that were the endpoints of the interval. How could I have found those values from what I was given? Well, 2 and 6 are the x-intercepts, or the zeros, of that function, right? And I know how to find zeros. I would just find it by setting that equal to 0. We call that the related equation. And so I could write my related equation as x squared minus 8x plus 12 equals 0, right? Almost the same, but instead of the inequality, we just use the equals. And certainly, the solutions to that would be the zeros of the function, which I find at the x-intercepts, the 2 and the 6. Now we can clearly see them graphically, but it wouldn't have been hard to find those analytically either, right? I could have just factored that trinomial. X squared would be x times x, sum of negative 8 and a product of 12, minus 2 and minus 6. And when I set the factors equal to 0, I could have easily gotten the 2 and the 6 by hand, right, analytically. So those two values are easy to find. The next part of the issue, though, is how do I know, once I find the 2 and the 6, where my function is actually less than or equal to 0, as opposed to perhaps greater than 0? In order to do that, I'm going to notice that the 2 and the 6 basically split my graph up into 3 sections. Oops. Here. And within each of the sections I've just defined, the graph is either above 0, below 0, or over here it's above 0 again. So each section is either above 0 or below 0. The graph only crosses the axis at those two zeros. Therefore, what I'll end up doing analytically when I can't look at the graph is I'll essentially pick a test value in each section, and I'll say if the test value is positive, I'll know the whole section is greater than 0. If the test value turns out negative, I'll know the whole section is less than 0, and I'll do that for each section of the graph. So, to solve the inequality analytically without using a graph, first we have to find the solutions to the related equation. And then secondly, we want to test an x value in each section of the number line as defined by these solutions. We're going to go through this kind of very carefully here for a couple of examples, so I think you'll be able to see exactly how that's going to work. All right, so let's give this a try. So I'd like to solve my inequalities, again, giving my answers in interval notation. We're going to work by hand, that is analytically, making sure that we justify the intervals we choose, and then we'll check by getting ourselves a Desmos graph so we can just look at it graphically like we did on the previous page. All right, first of all, my personal preference, I like to have one side be 0. I just think it's easier to test when I do that. So I'm just going to quickly rewrite this one as 2x minus 1 squared subtract 7 is greater than 0. Okay. Ultimately, that's going to be the inequality that I am looking to solve. My first step is to solve that related equation. So in the related equation, I'm just going to change my inequality into an equal sign. To solve this one, I'm thinking the square root method looks pretty good. I'm actually going to move the 7 back to the other side. And now that's set up perfectly to just take the square root on both sides. Remembering that plus or minus. Left-hand side just becomes 2x minus 1 equals plus or minus the square root of 7. I'm going to add the 1. So 2x will be positive 1 plus or minus the square root of 7. And then if I divide by the 2, I get 1 plus or minus the square root of 7 over 2. Now when I pick my test values, I probably is going to be a lot more convenient if I know the decimal approximations for those. So I'm going to get those right now. Let's see, I have 1 plus the square root of 7. Over 2. And then I have 1 minus the square root of 7 over 2. So my decimal approximation is approximately 1.82 and negative 0.82. All right, now I'm going to test my intervals. Those two x values, if I put them on a number line, essentially split that number line up into 3 sections, just like the 3 sections of the graph we looked at a moment ago. And I'm going to pick one test value in each section because I know each section either is going to be greater than 0, so it works, or is not going to be greater than 0, so it doesn't. Okay. So your test values, you can kind of pick whatever you want here. I'm going to go with -1, which certainly belongs over on this side. I need something between those two, so I'm going to go with 0. And then something bigger than 1.82, I'm just going to go with 2. All right, so let's see what happens. If I plug -1 back into the inequality that I'm trying to solve, I would have 2 times -1 minus 1 squared minus 7, which I want to be greater than 0. That would be -3 squared minus 7 is greater than 0. And 9 minus 7 is 2, which is greater than 0. So I'm just going to mark that with a true, or just a T if you like. My inequality is true in that whole section of the graph. I only had to pick one test value because it doesn't change from positive to negative within these sections. All right, let's try 0 next. I'm going to put that one down here. If I plug in x equals 0, I'm going to get -1 squared minus 7, which I want to be greater than 0, but 1 minus 7, of course, is -6, and that is not greater than 0. So that would make my whole inequality false in that entire interval. We're going to test one more. We're going to test the 2. 2 times 2 minus 1 squared minus 7, and I would like that to be greater than 0. That's 4 minus 1, or 3 squared minus 7. And indeed, 9 minus 7 is greater than 0. So the inequality is true in that part of the number line. Now, I've written out everything by hand here. I really have no problem, of course, with you using a calculator to do the arithmetic, but at a minimum, in order to justify your answers, I need to see what test value you've chosen, and I need to see what happened when you tried plugging it in. So at a very minimum, I would expect to see your test value and what happened when you plugged it in. If you're using technology to actually plug in the value, I have no problem with that. But show me what you're plugging in and what the result was, so I can see why you chose your trues and falses for each section. Now my final answer is going to be just the intervals that are true. So I have 2 places this time where my inequality is true. That would be from -infinity to -0.82. And I'm going to use a parenthesis this time since it's strictly greater than. And again from 1.82 to infinity. So that becomes my final answer. Now, I know it's a little bit of work to do this whole test interval thing. Again, if you use technology to help you with the arithmetic, it goes a little bit faster and you don't have to write down quite as much. But I really want you to master this technique, and I'm going to ask that you specifically use this technique when you do problems for me on homework and also on your tests. The reason for that is that this general approach of solving a related equation, putting the solutions on a number line, and then testing a value in each interval applies not just to quadratic inequalities, but it actually applies to all inequalities. So later in the course, when we do this for maybe cubic or quartic inequalities, or we'll get to some with logarithmic or square roots or all kinds of different inequalities, you won't need to learn a new technique. You'll be able to use the same exact technique. Solve the related equation, test a value in each interval. Okay? So at this stage of the game, I'm going to ask specifically that you learn this technique and show it to me when you do your homework and your test. All right, let's go ahead and just check this answer graphically. If I put my function that I wanted to have greater than 0 in here as y equals 2x minus 1 squared, whoops, that was supposed to be 2x, not x2. Minus 7. There it is. And we wanted this to be greater than 0. So I'm going to locate the zeros by clicking on the x-intercepts. There's my negative 0.82 and my positive 1.82. And you can see in this case, it's greater than 0 here before I get to the negative 0.82. So from negative infinity until I get to negative 0.82. Then it becomes negative for a while, which is not what I wanted. And then it's positive again from 1.82 out to infinity. Right? So graphically, this agrees with what we've seen or been able to show analytically. I won't necessarily check the graph on every single one of these, but I just wanted you to see that checking graphically is absolutely possible. All right, we have a couple more problems to look at. In this next one, I would like to know where is 5x minus x squared less than or equal to 0. So I'm going to start with that related equation. By the way, notice on this one I already had the 0 that I like, so I didn't have to do any changing around. And the related equation would be 5x minus x squared equals 0. I could factor a GCF out of this one. I can factor out an x. So I'd have x times 5 minus x equals 0, giving me x equals 0 and 5 minus x equals 0, which just gives me x equals 5. So there are the two solutions to the related equation. I'm now going to test the intervals that those two solutions create. Zero and 5. Okay. Creates kind of 3 zones or 3 intervals on my number line, and I need to test one value of x in each interval. So I'm going to go with -1. Oh, let's go with +3 and 6. Again, you got some free choice on those. As long as you pick within each interval, you're fine. All right, so I'm going to go back to my original inequality. That's what I'm testing. That's what I'm trying to decide whether it's true or false. if I plug in the negative 1, so 5 times negative 1, subtract negative 1 squared, and I want that to be less than or equal to 0, I have negative 5 minus 1 less than or equal to 0, and that's certainly true. Negative 6 is less than or equal to 0. My next test value is 3, so again I'm going to plug that back into the original here, and that would be 5 times 3 minus 3 squared, that I would like to be less than or equal to 0. 15 minus 9, that's 6, definitely not less than or equal to 0. And then finally, the last test point I picked was 6. So I'm going to plug that into the original. And that says 30 minus 36, or negative 6, is less than or equal to 0, so we are true again. So once again, this time I get 2 places where my inequality is true. From negative infinity to 0. And notice this time it is less than or equal to, so I'm going to use a bracket. And again from 5 to infinity, right out here. By the way, I didn't do this on the first one, but I should probably mention something notationally. A lot of time when we have 2 intervals and we're trying to kind of join the 2 pieces together to create one solution, we use this little union symbol. Just looks like a little U. And it just joins the 2 pieces of a solution together. All right, I'll leave it to you. If you want to check that one on Desmos, please feel free, but I'm going to go ahead and move on. All right, I've got one more for us to try before we get to a couple of word problems. So here's my original inequality. Once again, this one already has the 0, so I don't have to work for that. So I'm going to start out with that related equation. Which would be 4x squared minus 3x plus 5 equals 0. All right, if I'm going to solve this trinomial, so I'm thinking sum and product, I'd be looking for a sum of negative 3 and a product of 20. And I don't think I can do that. 1 and 20, 2 and 10, 4 and 5. None of those are going to give me that sum of negative 3. So I'm not going to be able to solve this one by factoring. So I am going to have to fall back on the quadratic formula this time. So let's see. Opposite of b would be minus the negative 3. Plus or minus the square root of negative 3 squared minus 4 times 4 times 5 over 2 times 4. So that's 3 plus or minus the square root of, let's see, that is 9 subtract 16 times 5 is 80. So that's negative 71. So I have imaginary solutions to my related equation this time. We've talked a little bit about imaginary solutions from a graphical perspective. We know that imaginary solutions do not appear on a graph of the function, right? We can't see any zeros excuse me, we have zeros, but we can't see any x-intercepts when we have imaginary solutions. So what this tells me is, since there are no x-intercepts, that means that this function is either entirely above the x-axis or entirely below the x-axis. So when I go to test, my entire number line is all one big interval. I can't put imaginary values on a number line, so there's no way to break this number line up. So I'm going to pick any test value and test it in my original. I strongly suggest 0 as a test value because 0 is really easy to work with, right? And if I go back to my original inequality and plug in x equals 0, I'm going to get 4 times 0 squared minus 3 times 0 plus 5, greater than or equal to 0. And indeed, 5 is greater than or equal to 0. So this is true, right? And it's going to be true everywhere. There are no separate intervals to check. So I check any one place, it's true. And my solution is going to be all real numbers from negative infinity to infinity. By the way, if this had turned out false, then there would not have been any solutions to the original inequality. So quick note, if I had been asking, is 4x squared minus 3x plus 5 less than 0, right, then that would have been never, right? Turns out it's always greater than 0. And so this one would have no solutions. Let's just take a minute and look at that one graphically. If I graph my function, you can see it does indeed exist entirely above the x-axis, so the y values are always greater than or equal to 0, no matter what axis. All right, let's do a couple of applications that involve inequalities. In example 3, we're actually going to build on a situation that we started in the last section. Remember how we had the quadratic function that modeled the ball that was getting thrown up into the air and then allowed to come back down and land again, right? My model, my function that allowed me to figure out the height at any particular time was 96t minus 16t squared. We're measuring time in seconds, and the height is in feet. Now, this time I'm going to ask a slightly different question. Suppose there's a nearby building with a window that's 80 feet off the ground. Write an inequality that represents the situation in which the ball is above the level of the window. So I need to know, when is that ball at a height that's more than 80 feet? So I want h of t to be greater than 80, or in other words, I want 96t minus 16t squared to be greater than 80. So I've just expressed that statement as an inequality. I'd now like to solve that inequality to actually figure out what time interval, or intervals, the ball is above the level of the window. We must justify our interval without using a graph, though we can always check with a graph, which we're actually asked to do in part C. So I'm going to start with my related equation again. make that equal to 80. And again, I really prefer a positive leading coefficient, so I'm going to add that to move it over to the other side. So I'm going to subtract the 96t and add the 16t squared to get my 0. So I'd have 16t squared minus 96t plus 80. All right, I believe these numbers were probably somewhat artificially chosen to all be divisible by 16. So let's factor out a 16. That t squared minus 6t plus 5. And this time, I'm thinking that probably does factor sum of negative 6, product of 5, negative 1 and negative 5. So I now have 1t squared, got to be t times t, minus 1 minus 5. No variable out here, so this does not contribute to the solution for t. But I would have t minus 1 equals 0, and I would have t minus 5 equals 0, giving me t equals 1 and t equals 5. Now logically, I know when I think about what this thing's going to look like, right, it goes up and back down, that if there's a window here at height of 80, the part that we're above the window logically really has to be between the t equal 1 and the t equal 5, right? It wouldn't make sense for it to be above 80 in the first or last part of its flight. But again, we're supposed to justify the interval without using a graph, so I'm going to do it analytically, but I'm expecting to get an answer of 1 to 5, between the times of 1 second and 5 seconds. But let's check that. And let's see. What we're actually testing is the inequality that we wrote up here. We want to decide whether that's true or false for a test value within each interval. So I'm going to test 0, I'm going to test 3, and I'll test 6. Now, I actually didn't get this one to have 0 on one side, but you know what? We could still do it, right? Mostly I like to do that, but I didn't this time, so let's just see how it works. If I plug in the 0, I'm going to get 96 times 0 minus 16 times 0 squared greater than 80. That says 0 greater than 80, which is clearly false, and that's what I expected. For any time before 1, I should still be down in this part of the flight. Right. I'm expecting to get a true value in the second part. That's when I'm up here at the very height, the tallest parts of my flight. So that would be 96 times 3 minus 16 times 3 squared, hoping that's greater than 80, and that's more than I want to do in my head. That's 144, which certainly is greater than 80. So as expected, this section from 1 to 5 is true. And then we're going to expect to get false again for anything bigger than 5, but I'm going to go ahead and try the 6. 96 times 6 minus 16 times 6 squared greater than 80. Sorry, I got to squeeze that in. And I'm going to try that again on Desmos. 96 times 6 minus 16 times 6 squared is 0 again. So this says 0 greater than 80, which certainly is false. Again, none of this is unexpected. I'm just now showing that I can get the same result analytically as I expected from kind of a visual graph in my head. So this is true from 1 second to 5 seconds, or on the interval from 1 to 5. Right, it was just greater than, not greater than or equal to, so I did use the parentheses rather than the brackets. All right, and then part C says verify that conclusion using a graph. Let's see. I'm going to go ahead and do this one the way it was written. I kind of did forget to bring the 80 over and make it greater than 0, so I'm going to show this to you two ways. I could actually use it the way it's written. I could go ahead and put in my 96, y equals 96t, minus 16t squared. And then I could put in y equals 80. Goodness, can't type today. There we go. Oh, I'm going to set my caps lock on. Let's make those lowercase y's so it understands what I'm talking about. There we go. There's the t equal 1. There's the t equal 5. And you can see we're above the 80. Oops, in between the 1 and the 5. Alternatively, I could have remembered to change this and bring the 80 over and said this is 96t minus 16t squared minus 80 is greater than 0. And then I would have been able to just do it with the intercepts. And notice now, I'm back to the t equal 1 and the t equal 5, giving me 0, and this is greater than 0, in between 1 and 5. So it does work either way. I intended to originally remember to move the 80 over and do it this way. I just find that going ahead and using the intercepts every time makes it a little easier for most students to remember, so my apologies for forgetting to do that. All right, we have one more problem. And again, this kind of goes back to a problem that we started last time. You remember the Toyota Camry problem, where we were talking about finding the driving speeds that would give us a fuel economy of at least 22 miles to the gallon. So last time, we had started with our data here for various speeds. We had the fuel economy given, and we just used a quadratic regression to come up with that equation, or that function m of v, that gave the mileage or fuel economy for whatever speed you happen to be traveling. So I'm just going to go ahead and write that function down over here so we can use it. We had m of v was negative 0.017 v squared plus 1.905 v minus 24.864, where v was our speed and m is the fuel economy. All right, so we're going to use that same model, and this time our goal is to find out what speeds you could drive at that would give you a fuel economy of at least 22 miles per gallon. So we want our fuel economy, M of V, to be at least 22, or in other words, it can be greater than or equal to 22, right? If it's equal to 22, it's at least 22. And if it's anything bigger than 22, it's at least 22. So I'm going to put my function in here. And I want to know where that's greater than or equal to 22. Now this one says we are allowed to use technology, so thank goodness with these rather unpleasant numbers, we don't have to mess with this by hand. I am going to remember this time to get the 0 that I like on this side, so let's just subtract the 22 to start with. That would make that negative 46.864. And I would like to know where that's greater than or equal to 0. And I'm going to do this one with technology, so I'm going to do it visually with a graph. So this time I'm graphing y equals, and I'm going to type in that function. All right, and clearly I don't have a very good window, so let me go. That's a bit better. All right, again, we'd already said we want to know where this is greater than or equal to 0. So if I find my x-intercepts here, this is greater than or equal to 0 in between those two values. So I'm going to say my solution starts at 36.47 and ends at 75.59. So there's the interval. And again, it was this part that was greater than or equal to 0 is what we were looking at. And I just took those two values right off the graph. All right, to put this in terms of the problem, the question was to find the driving speeds that would result in this fuel economy of 22 or better. So these are driving speeds. We'd have to say we want to drive between 36.47 miles per hour and 75.59 miles per hour. I wouldn't argue with anyone who just wanted to round those to the nearest whole number, because we don't usually think of our driving speeds in quite that detailed terms, right, in terms of decimals, so 36 to 76 miles per hour, basically. I guess at 76 we're a little over. Maybe we should go with 75. All right, so that brings us to the end of section 3.6.